This is question 0B, part C, where we are trying to interpret the index K of the DTF coefficients Ck. So we know that K is equals to 0 to n minus 1, and we want to know exactly what different values of K means in terms of the actual digital angular frequency omega, which is radian per sample. So in this question, we have already seen using n equals to 40 for Ck to solve for this equation. Now we are going to use n equals to 200. Let's first revise what does Ck means in the horizontal axis. Take a look at this PDF, Tutorial 6A, Question 0B, Part C, Interpreting Index K. I've written down the answers here. I would now use this writing to explain the question. Now, this is the spectrum, the magnitude spectrum, and this is the horizontal axis. And typically in the spectrum, we are interested in the values from 0 to 2 pi, or 0 to pi, or from minus pi to pi. In the DTFS, it will divide this spectrum into n parts. And each of these, this is the C0, and the next one is C1 and C2. And the interval in between them is 2 pi divided by n. And then you will now see that you will reach here. The last one is Cn minus 1. And then to reach 2 pi, it will be Cn. And you'll now realize that Cn and C0 are exactly the same value because the magnitude spectrum is 2 pi periodic. Now, sometimes I will use small omega or big omega, so it really depends on the notation. In this case, I should have written it as big omega to denote the digital angular frequency radian per sample. Some common notation. If I use big omega 0, this is the fundamental digital frequency, which is 2 pi divided by n. You can also use this diagram to visualize the change of the angular frequency. In here, it is the complex plane. And then what we have done is that I'm going to sketch for you the unit circle. And then now we begin to see the different phases. And the phases are changing with respect to 2n over, the frequency is changing with respect to 2 pi over n. That means at each step, when k goes from 0 to 1 or 1 to 2, this delta here, or this theta here, is 2 pi over n radians. And here k is the step. So now we come back to answer the question where n is equals to 200. What will happen? So basically, we're dividing from 0 to 2 pi, 200 different small lines. So now you will see that we have many of these bins here. So the question now is, where are the spectral lines for different CKs for this question? In our question, we have omega equals to 0.15 pi. Now to reach 0.15 pi, you have to let k equals to 15, because 2 pi over 200, which is 2 pi over n, times 15 is 0.15 pi. And now at index k equals to 15, so this axis here is k equals to 0 to n minus 1, which is 200. At C15, so this actually should be k. At C15, our amplitude is 1. This represents the y2 term, which is minus 1 ej 0.15 pi n plus pi over 2. Hence, the phase shift now is this guy, which is, now the second term is minus 1 ej 0.15 pi n plus pi over 3. I'm going to write this as this notation here. where -1 with the phase shift of plus pi over 3, of course with the n 0.15 pi n. Now we're going to move the minus into the phase, so it'll be 1 plus pi over 3 minus pi. Now we are going to work out this. Pi over 3 minus pi is of course pi over 3 minus 3 pi over 3, which is minus 2 pi over 3, which is minus 2.0944. So here it shows that the magnitude is 1 and the phase is minus 2.0944 at C15, which is this value here. So this is the magnitude and this is the phase for Y2n. So the take-home message is this: as we increase n from 40 to 200, so in the previous example it was 40, and this was the magnitude and the phase, and it was sitting at C3. Now C3 has become C15 because we have now basically divided the 2 pi into 200 parts. That's the answer. The rest is the same. They are all moved by how many? 5 times the index. So now is 30. Previously it was, the index was 6. Okay, thank you.